started. So till in the last class we discussed about the Coulomb's law and its applications. We would continue with the Coulomb's law, but this time in the previous lesson we have discussed Coulomb's law only when two forces, only when two charges are interacting. No? Now we are going to study about Coulomb's law. In Coulomb's law we'll study about when a number of charges are interacting, then what happens to the force, okay, electrostatic force. So we call it as principle of superposition. What happens to the electrostatic force when a number of charges are interacting? Alright? Yes. If only two charges are interacting, say Q1 and Q2, we have studied in Coulomb's law, like if only two charges are interacting, then this charge will experience a force due to this charge, and this charge will experience an electrostatic force due to this charge, right? Only that. But what happens if a number of charges are interacting and you want to find out the total force that is exerted on one particular charge due to all these charges? So the principle of superposition is going to give us that result, okay? The resultant electrostatic force. So principle of superposition says that when a number of charges are interacting, then the total force on a given charge will be the vector sum. Not if you consider it only in magnitude, then you can say algebraic sum, okay? But if we consider the direction, then you have to take the vector sum. So when a number of charges are interacting, the total force on a given charge will be the vector sum of all the individual forces that is exerted on this charge by all the remaining charges. That's the principle of superposition. Are you following that? If we consider only in magnitude, then when a number of charges are interacting, the total force on a given charge will be given by the algebraic sum of all the forces that is exerted on this charge by all the other charges, okay? But when we consider in vector form, we have to take the vector sum of all the forces. Are you getting that? All right. So when a number of charges are interacting, the total force on a given charge will be the vector sum of all the forces exerted on a given charge by all the other charges. So suppose there is a charge Q1 placed in free space, charge Q2 placed in free space, charge Q3 placed in free space, and so on up to charge Qn placed in free space. Alright? So there are n number of charges interacting with each other. Let's consider that all of them are positively point charges, positive point charges. Alright? They can be like charges, they can be unlike charges, okay? But in order to make things easier, we can consider that all these charges that are interacting are point positive charges only. Okay? Now see, so a number of charges are interacting from Q1 up to n, okay? N number of charges are interacting, and suppose I want to find out the total electrostatic force on this charge Q1 due to all these charges, okay? N number of charges are interacting. If I want to find out the total force on Q1, okay, then I have to find the vector sum of all the individual forces that is acting on this Q1, alright, by all these charges. Now see, I'm going to find here the total force on Q1. Then see, Q2 will exert a force on Q1, right? Now, let me write Q1 over here, okay? Q2 will exert a force on Q1, and that force will act in this direction. Repulsive force, because all of these charges are point positive charges. Let the distance between the two charges be R, 1, 2. And let the force acting on Q1 due to Q2 be F, 1, 2. Alright? Now Q3 is also going to exert a force on Q1. So Q3 will also exert a force on Q1, and that force will act in this direction, repulsive force. Let that force be F, 1, 3. Let the distance between the two charges be R, 1, 3. Alright? Now Qn, Q4, Q5 and so on up to Qn. Qn will also exert a force on Q1, and that force will act in this direction, repulsive force. Let me denote this force by F1n, and the distance between the two charges is R, 1. Okay. Now, in order to represent the direction of the force, we need a unit vector. Unit vector is a vector of magnitude 1 which represents direction. So let unit vector R1, 2 cap. Let's say it's no space, so let me write here. Very difficult. Okay. Let unit vector R1, 2 cap represent the direction of the force F1, 2. Alright? Let R, okay, let R1, 3 cap represent the unit vector, be the unit vector representing the direction of this force F1, 3. And so on. And let R1n cap be the unit vector representing the direction of the force F1n. Alright? Then according to superposition principle, the total force exerted on Q1 will be given by the vector sum of all the forces exerted on this charge Q1 by all the other charges, right? So those forces are F12, F13, F14, F15, similarly up to F1. Is it okay? So using Coulomb's law, I'm going to find all these individual forces, and I'm going to find out their vector sum. Alright? Now according to Coulomb's law, the electrostatic force that is present in between charge Q1 and Q2, so F12, will be given by what? 1 upon 4 pi epsilon naught into Q1, Q2 upon, what is the distance between the charge Q1 and Q2? R12, right? So R12 square, okay? And the unit vector representing the direction of the force F12 is, the unit vector representing the direction of the force F12 is R12 cap. Similarly, I can find out the force, using Coulomb's law, I can find out the force acting on Q1 due to Q3. Similarly, we can write F13 is equal to 1 by 4, why epsilon naught? Because we have placed the charges in free space. So epsilon naught is the permittivity of free space, okay? Into Q1, Q3 by distance, square of the distance, R13 square unit vector, R13 cap. And so on. Vector F1n will be 1 by 4 pi epsilon naught into Q1, Qn upon R1n square unit vector R1n. Alright? Now I'm going to add all these forces. F12, 1 by 4 pi epsilon naught into Q1, Q2 by R12 square with unit vector R12. plus F13, your first F13, 1 by 4 pi epsilon naught into Q1 Q3 by R13 square with unit vector R13, and so on. And then force acting on charge Q1 due to end charge due to Qn will be given by 1 by 4 pi epsilon naught into Q1 Qn by R1n square with unit vector R1n. Alright? Now let me take some common terms. 1 by 4 pi epsilon naught is common everywhere, right? Charge Q1 is common everywhere. So 1 by 4 pi epsilon naught Q1, and then what do we have? Q2 by R12 square with unit vector R12. Here we have Q3 by R13 square with unit vector R13, and so on, plus we have Qn by R1n square with unit vector R1n. Is it okay? So this expression gives you the total force that is exerted on charge Q1 due to all the other charges. Similarly, if you want to find out the total force on Q2, now, then Q3 will exert an electrostatic force of attraction on Q2, Q1 with Q2, Q3 with Q2, Q1 with Q2, Q4 with Q2, Qn with Q2. And you need to find out the vector sum of all the individual forces. Similarly, if you want to find out the resultant force that is acting on this end charge, then you need to find out the vector sum of all the other charges from 1 to n minus 1 charges that is acting on this Q1. Alright? So this is the resultant expression. Okay? So this is known as your superposition principle. Alright? Okay. Now, we have to do a numerical basing on this. Okay, it will come a bit later. The next one is continuous distribution of charge. Distribution of charge. How can a charge be distributed over a body? Till now we have considered only a point charge, alright? Like an electron, like a charge of an electron. Electron is just a point particle, so charge of an electron. Proton is just a point particle, right? So charge of an proton. That is what we have discussed till now, a point charge only. But now let us discuss, like, if we have a charged body, then how will the charges be present on that body? Okay, yes. So distribution of charge. Distribution of charge. This is what we have to see now. Let's say like this. Consider a body in the form of a rod. In the form of a rod of length L. So we have a body in the form of a rod of length L. Now this rod has a total charge Q. Then this charge Q will be uniformly distributed along the entire length of this rod. Then we can find out what is the charge density of this rod. Charge per unit length. Is it okay? Yes. So a charged body can be in the form of a rod. If a charged body is in the form of a rod, okay, linear, one-dimensional, okay, then in that case, the charge will be distributed uniformly along the entire length of the rod. Are you following that? Now, a charged body can be in the form of a sheet, like your paper, like the surface of this whiteboard, right? Okay, a metallic sheet. A charged body can be in the form of a sheet. Suppose it has area A. There is a charged body of area A in the form of a sheet of area A with total charge Q. Then if a charged body is in the form of a sheet having some certain area, then this charge will be uniformly distributed all over its surface. So we can find out its surface charge density. Surface charge density means, okay, charge distribution per unit area. Are you getting that? Okay. In 1 square meter area, how much charge is accumulated density? Okay. Now a charged body can be in the form of a sphere, in the form of a cylinder, in the form of a cuboid or cubes, right? In the form of a sphere or spherical shell. Then in that case, how will the charge be distributed? So suppose there is a body in the form of a sphere occupying a volume V. Q is the total charge of this body. Then in that case, the charge will be uniformly distributed. This charge Q, it will be uniformly distributed over the entire volume of this sphere. Are you getting me? So this is how distribution of charge takes place on large bodies. Okay? Till Coulomb's law, till the principle of superposition, we are discussing only about the point charges. Okay? So all the charge will be accumulated at this point only, right? But when we talk about larger bodies, 1-dimensional, 2-dimensional, 3-dimensional bodies, then this is how charges are being distributed. Are you getting me? Yes. So the first one is linear charge density. Linear charge density. Consider a rod. Consider a charged body in the form of a rod of length L having charge Q. Then this charge Q will be uniformly distributed over the entire length of this rod. When we consider a rod, okay, a very thin rod, just 1-dimensional, okay, if it is only 1-dimensional, just a line having negligible thickness, then the charge cannot be distributed over its surface, right? The charge cannot be distributed over its area of cross-section. It can be distributed only along the length of this rod. Is it okay? So the surface, so the linear charge density, we denote by lambda, is given by total charge distributed, total charge per unit length, Q upon L. So this Q upon L is known as your linear charge density. Are you getting that? Yes. Now, number B, surface charge density. Consider a body in the form of a sheet having area A and total charge Q. Then this charge will be distributed uniformly all over its surface only. Is it okay? So we can find out its surface charge density denoted by sigma. So surface charge density is defined as total charge upon area. Alright? And when we are considering about a volume charge density. Volume charge density. If your charge body is in the form of a sphere, 3-dimensional, if your body is 3-dimensional, so suppose consider a sphere having volume V and total charge Q, then this charge Q will be uniformly distributed over the entire volume of this sphere. Then the volume charge density rho is given by total charge upon the volume of the sphere. Okay. If this is the volume of the sphere, then of radius r, then I can write what? 4 pi r cubed. If this is a square sheet, then Q upon area we can write side square. Alright? Rectangular sheet, then length into breadth. And for this one-dimensional is just the length. We have only the length. Alright? So this is how distribution of charges takes place in one-dimensional, two-dimensional, and three-dimensional. Is it okay? Yes. I think you need to take a note on both these topics, and then we will start with the next. Alright? You can take a note on this too. Write something about it.